The night sky, as captured by the James Webb Space Telescope, is not a static field of diamonds. It is a river of light, a slow-motion ballet of photons, some of which have been travelling across the universe for over 13 billion years. On a seemingly unremarkable Tuesday afternoon at the Space Telescope Science Institute in Baltimore, a computer algorithm was doing what it always does, sifting through the endless torrent of data pouring down from Lagrange Point 2. It was comparing images, looking for differences, hunting for the ghostly flicker of something that wasn't there before. And then it found one. A single pixel, buried deep in a field of 100 million others, had changed. It was just a little bit brighter than it had been in the previous observation cycle. That tiny, almost imperceptible shift in digital brightness triggered an automated alert. It pinged a server, it logged a timestamp, and it changed everything. You have to understand the stakes here. This is not some university telescope that cost a few $100,000. This is the James Webb Space Telescope. The $10 billion, 25-year-long gamble that scientists took to see the universe as it was when the very first stars turned on. For decades, catching a supernova in its earliest moments was a holy grail. We had seen the aftermaths. We had seen the expanding clouds of gas, the neutron stars spinning away inside ancient remnants. But the moment itself, the actual detonation, that was always a ghost story, told long after the event had faded. We were always late to the party, until that alert. In the control room, the initial reaction was not excitement. It was skepticism. Supernovae happen all the time. But catching one with a telescope pointed at a specific target, at the exact right millisecond, is like catching a single drop of rain in a hurricane with a full. The scientists pulled up the raw data. They ran the diagnostics. They checked for cosmic rays hitting the detector, for a glitch in the software, for anything mundane that could explain the anomaly. But the numbers held. The light curve was unmistakable. It wasn't a steady glow, it was a flash, a sudden, violent spike in brightness that then began to cool. This was not a variable star. This was not a mistake. This was the first light of a stellar explosion, captured in real time. I want you to really think about what that means. A star that existed in a galaxy cluster called Abell 2744, a region of space so far away that the light we were seeing had left its home before the Earth even had its first continents. That star lived its entire life, burned through its nuclear fuel and reached the end of its rope in a cataclysmic collapse. And for the first time we had a front row seat. The scientists in that room watched the data stream in. They saw the temperature of the explosion rise to billions of degrees. They saw the shockwave begin its journey outward through the vacuum. It was happening right there, on their screens, in something close to real time. The silence in the room broke into a hum of disbelief. People started calling colleagues. The lead investigator just stared at the screen, refreshing the data feed, waiting for it to be taken away. But it wasn't. It was real. The James Webb Space Telescope had done what no telescope before it could do. It had captured the exact moment a star died. And that is where we have to pause and ask ourselves a very human question. What does it actually mean to watch a star die? We think of death as an ending, a finality. But in the cosmos, the death of a star is the most creative thing that can happen. It is the only way that heavy elements get forged and spread across the universe. Every atom of calcium in your bones, every atom of iron in your blood, was forged in the heart of a star just like this one. We are literally watching the ingredients of future planets, future life, being cooked up and thrown into the cosmos. But this specific event, captured so perfectly by Webb, holds secrets we haven't even begun to unlock yet. The light we saw wasn't just one quick flash. There were echoes. There were distortions. The gravity of the galaxy cluster Abell 2744 acted like a giant lens, warping the fabric of space-time around the explosion. This meant that we didn't just see the supernova once. We saw it multiple times, arriving from different bent paths of space, like light echoing around a canyon. This gave the astronomers a kind of time machine, allowing them to watch the same explosion play out from different angles. Imagine watching a movie where you can rewind and see the same scene from the camera of the villain, then the hero, then the bystander, all at once. That is what the lensing effect did for this supernova. The data is so rich, so layered, that it might take years for theorists to fully understand what it has revealed about the nature of gravity, dark matter, and the explosive mechanics of stellar death. The automated alert systems are getting smarter. They are learning to spot the needle in the haystack. But the story of this catch is not just about a smart computer. It is about a generation of scientists who bet their careers on a telescope that almost got cancelled, a telescope that was once called the telescope that ate astronomy. And that telescope, sitting out in the cold dark 1 million miles from Earth, just blinked. And it saw a star say goodbye. So the question is not just scientific, it is philosophical. When we watch a star die, are we watching an end, or are we watching a beginning? And what happens to the fabric of our own reality, our own sense of permanence, when we realize that the universe is a place where these explosions are happening constantly, every single second, and we are only now, for the first time, learning how to truly look? And that brings us, quite literally, to the machine, the telescope that has to see through time itself, the James Webb Space Telescope. It is without question the most ambitious piece of engineering ever sent beyond the orbit of the Moon. But here's the thing about Webb. It doesn't just look at the sky the way Hubble does. It was built for a different kind of light, light our eyes can't see, light that carries the fingerprints of the universe's very first moments. And to do that, it had to become a cold, dark, impossibly stable observatory floating 1 million miles from home. Let's talk about that orbit for a second, because it's not just a parking spot. Webb doesn't circle Earth like Hubble. Instead, it sits at a point in space called L2, the second Lagrange point. Imagine a gravitational balancing act between the Earth and the Sun, a place where the pull of both bodies cancels out just enough that a spacecraft can hover there, using almost no fuel to stay put. It's a quiet, stable corner of the solar system, but it's also incredibly remote. 1 million miles away, which means if something breaks, if a mirror gets misaligned, if a sun shield tears, there is no repair mission. No astronaut is going to fly out there with a wrench and a roll of duct tape. This telescope had to work perfectly on the first try, or it would become the most expensive piece of space junk we ever built. And the engineering required to achieve that perfection is frankly mind-boggling. Start with the sunshield. It's the size of a tennis court, about 70 feet by 47 feet. But it's not a solid sheet of metal. It's 5 layers of a material called kapton, each one thinner than a human hair, coated with aluminum and silicon to reflect heat. The analogy that sticks with me is this. Imagine sitting in front of a blazing campfire, holding a piece of paper between you and the flames. That single sheet of paper would protect your face from the direct heat, but you'd still feel the warmth. Now imagine stacking 5 of those papers, each one spaced just a few inches apart, and painting them with a mirror finish on both sides. By the time the heat passes through all 5 layers, the temperature drop is staggering. The sun-facing side of Webb's shield is about 230 degrees Fahrenheit, hot enough to melt soldering lead. The side facing the telescope is negative 390 degrees Fahrenheit, colder than the surface of Pluto. That is not a typo. 230 on one side, nearly 400 below zero on the other. The same structure, separated by only a few feet of vacuum and some incredibly clever engineering, maintains a temperature difference of over 600 degrees. Why is that so critical? Because Webb is an infrared telescope, and infrared is heat. If the telescope itself were warm, its own heat would swamp the faint infrared signals coming from distant galaxies, like trying to hear a whisper in a jet engine factory. The colder the telescope gets, the more sensitive it becomes to the faintest whispers of the early universe. And then there's the mirror. The primary mirror is 6.5 meters across, nearly 22 feet, which gives it about 6 times the light-collecting area of Hubble. But a mirror that large couldn't be launched in one piece. No rocket fairing in existence is that wide. So the engineers built it in segments, 18 hexagonal beryllium mirrors, each one coated with a microscopically thin layer of gold. Gold is actually a terrible mirror for visible light, but for infrared, it's the best reflector we have. Those 18 segments had to unfold in space, align themselves to within a fraction of the width of a human hair, and then hold that alignment perfectly, despite being shaken by rocket vibrations, baked by sunlight on one side and frozen on the other. The entire telescope sits on a massive structure made of carbon fiber composites, materials that barely expand or contract with temperature changes. Even then, the alignment process took months. Engineers had to nudge each segment by nanometers, using tiny actuators, until the entire mirror acted as a single flawless surface. Why go through all that trouble? Why not just build a bigger Hubble? Because visible light doesn't tell the whole story. Visible light gets blocked by dust. The universe is full of giant clouds of gas and dust. The cocoons, where stars are born. The shrouds around dying suns. The vast sheets of interstellar debris that hide the most interesting objects from our view. Infrared light, with its longer wavelength, slips right through that dust. It's like hearing a conversation through a thin wall instead of trying to read lips through a keyhole. And more importantly, infrared light is the light of the distant past. As the universe expands, the light from the first stars and galaxies gets stretched. The wavelengths get longer, shifting from ultraviolet and visible light down into the infrared. By the time that light reaches us, over 13 billion years later, it has been redshifted so much that only a telescope like Webb, built to see infrared, can detect it at all. So when we say Webb is a time machine, we're not being poetic, we mean it literally. It sees objects as they were, not as they are. Look at a galaxy 10 billion light years away, and you're seeing it as it existed 10 billion years ago. The deeper Webb looks, the further back in time it goes, and the further back it goes, the closer it gets to the very beginning. In July of 2022, after months of alignment and calibration, the first images were released to the world, and the world held its breath. The images were breathtaking, but not because they were the deepest or the sharpest. Hubble had taken deep fields before. What made Webb's first images so stunning was the sheer volume of galaxies they revealed. The first deep field, a patch of sky the size of a grain of sand held at arm's length, contained thousands of galaxies, many of them never seen before. Among them were galaxies from just a few 100 million years after the Big Bang. Galaxies that looked surprisingly mature for their age. The models had predicted they would be small, chaotic, irregular blobs. Instead, Webb showed us structures that looked like barred spirals and grand design spiral arms, as if the universe had figured out its architecture much faster than anyone expected. It was the first hint that our theories of early galaxy formation needed rewriting. And then came the exoplanet science. Webb turned its gold-plated mirror toward a planet called WASP 39b, a hot gas giant 500 light-years away. By analysing the starlight passing through the planet's atmosphere during a transit, Webb detected the unmistakable signatures of carbon dioxide. This was the first time CO2 had ever been detected in an exoplanet atmosphere. It was a huge milestone, not just because it proved Webb's spectroscopic capabilities, but because it showed we could directly measure the chemical composition of worlds around other stars. And where there's CO2, there might be water, and where there's water, there might be life. But there was one kind of observation that Webb had not yet made. One promise that remained unfulfilled. When a massive star ends its life, when it collapses and then rebounds in a catastrophic explosion, the first flash of light is not the bright, lingering glow of the supernova we know from Hubble images. It's a shock breakout, an intense burst of X-rays and ultraviolet light that lasts only hours, sometimes minutes. This shock wave tears through the star's outer layers at tens of thousands of kilometers per second, and when it breaks through the surface, it sends a pulse of light racing outward. Catching that moment, the exact instant when a star becomes a supernova, is one of the holy grails of astronomy. Hubble never managed it. Ground-based telescopes were always a few hours too late. The signal was too fast, too faint, too easily missed. Astronomers had theoretical models of what shock breakouts should look like, but they had never, not once, directly observed one. Not until Webb. The setup for this discovery was almost accidental, a perfect storm of planning and dumb luck. The survey was called the JWST Advanced Deep Extragalactic Survey, or JDES, but the specific target was a galaxy cluster known as Abell 2744. This cluster is a gravitational lens, a vast concentration of mass that bends and magnifies the light from galaxies behind it, acting like a cosmic telescope, a natural one built by gravity itself. Because of this lensing effect, the galaxies in the background appear stretched, magnified, sometimes by a factor of 10 or more. It's a way to see even deeper than Webb normally could. The routine observation was simple. Take a series of infrared images of the same field of view, spaced out over a few months, to look for changes, for objects that moved or brightened. Basically, a time-lapse of the distant universe. The astronomers were looking for variables, for distant supernovae that had exploded billions of years ago and whose light was just now reaching us, bent and magnified by the cluster. They expected to find a few dozen, maybe 50, over the course of the survey. What they didn't expect was to catch one in the act of turning on. Imagine you're staring at a long-exposure photograph of a busy street at night. You see the steady lights of street lamps, the blurred streaks of car headlights, the distant glow of building windows. But then, in one frame, a tiny dot appears where there was nothing before. In the next frame, it's brighter. The frame after that, it's already starting to fade. That dot appeared and then disappeared within a handful of images, a transient flash too brief for any telescope to have captured before. But Webb was watching. The telescope, with its enormous mirror and its cryogenic stillness and its eagle-eyed infrared vision, had recorded the moment when a massive star, some 11 billion light-years away, ended its life. The shock breakout had been seen, not predicted, not modelled, not hypothesized, but actually, definitively, captured by human eyes for the first time in history. The detection happened not in a moment of dramatic real-time discovery, but in a quiet office at a computer screen, during a routine data processing run. An astronomer, probably tired, probably drinking cold coffee, scrolling through stacks of images, noticed an anomaly. A point of light that was bright in the first few exposures, then dimmed, then vanished entirely. Most of the supernovae they expected would take weeks to fade. This one was gone in days. That was the signature of a shock breakout. The fast rise, the sudden brightening, then the rapid decline as the blast wave expanded and cooled. They had caught the universe in the middle of the most violent event it can produce. And they had done it with a telescope that was never specifically designed for that task. This is where the story shifts from the technical marvel to the cosmic drama. The telescope that sees through time had finally done what no other instrument could. It had watched a star die in real time, 11 billion years later, and it had done so almost by accident, because of a routine observation of a galaxy cluster that just happened to be aligned in a way that magnified that specific point in space. That kind of alignment, that combination of perfect timing and cosmic geometry, happens once in 100 opportunities, maybe less. And Webb, in its first full year of science operations, caught it. The question now is not whether Webb can see the universe's most violent moments. The question is, how many more of these shocks are out there, waiting to be seen? And what they will tell us about the way stars end, the way elements are scattered, the way the cosmos recycles itself over billions of years. So buckle up. because we're about to walk through that discovery blow by blow. The star, the explosion, the data, and the implications. The moment the telescope that was built to find the first light of creation captured the final light of a dying sun, and what it means for everything we thought we knew about the death of stars. But before we get to the James Webb Space Telescope's big moment, we need to talk about what it was actually looking at. Because honestly, a supernova isn't just a star going boom. It's the most violent event in the universe that we can actually witness. And I mean that literally. In those first few seconds of the explosion, a single supernova releases more energy than our Sun will produce over its entire 10 billion year lifetime. Think about that for a moment. The Sun, that giant ball of nuclear fire that has been shining for 4.5 billion years and will keep shining for another 5 billion, has less raw power in its whole existence than a supernova has in a handful of heartbeats. That is the scale we're dealing with. It's not just big, it's incomprehensibly, almost absurdly, violent. Now, there are two main ways a star can die this spectacularly, and they are like two completely different flavors of cosmic destruction. The first one is what we call a core collapse supernova, and it happens to the big guys, the real heavyweights. We are talking about stars that are at least 8 times more massive than our Sun. For these monsters, fusion is a race against gravity. The star spends millions of years fusing lighter elements into heavier ones, building up layers like an onion. Hydrogen turns into helium, helium turns into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and then eventually you hit iron. And iron is a problem. Fusion usually releases energy. It's what keeps the star inflated against gravity's constant pull. But when you try to fuse iron, it does the opposite. It consumes energy. So the moment a massive star's core turns into solid iron, the engine stops. Gravity, which has been patiently waiting for billions of years, finally wins. The core collapses, and I mean collapses. At speeds approaching a quarter of the speed of light, the innermost part of the star squeezes down into a neutron star, just a ball of pure nuclear matter 20 kilometers across, and then all the infalling material slams into this newly formed, rock-hard surface. It bounces back. That bounce, that shockwave, rips the rest of the star apart in a detonation that outshines entire galaxies. Then you have the other kind, the thermonuclear supernova, which astronomers call Type Ia. This one doesn't happen to a single star. It happens to a dead star. When a star like our Sun runs out of fuel, it doesn't collapse into a black hole. It turns into a white dwarf, a super-dense, Earth-sized cinder made mostly of carbon and oxygen, slowly cooling off for eternity. But if that white dwarf has a companion star orbiting it, it can start stealing material. Over thousands or millions of years, it pulls so much gas onto its surface that it eventually hits a critical mass limit, about 1.4 times the mass of the Sun, which astronomers call the Chandrasekhar limit. At that point, the pressure and temperature in the core becomes so extreme that the entire star ignites in a runaway thermonuclear chain reaction. The whole thing blows itself to smithereens in seconds. Not a single atom of the white dwarf remains. It is completely vaporized. And because Type Ia supernovae all happen at essentially the same mass, they all have roughly the same brightness. This makes them incredibly useful as standard candles for measuring cosmic distances. But for our story today, we are primarily talking about the first kind, the core collapse, the monster that ripped itself apart. Now, here is where it gets tricky for astronomers. That whole explosion I just described, that violent chain reaction from collapse to detonation, happens in seconds. But the first flash of light that escapes the star happens a little later, and it only lasts for minutes to hours. We call that fleeting moment the shock breakout. The shock wave I mentioned earlier, as it plows through the outer layers of the star, takes some time to reach the surface. The star is huge after all. A red supergiant, the kind that makes iron cores, can be 1 billion kilometers across, big enough that if you put it where the Sun is, it would swallow Jupiter. So when that shock finally punches through the outer skin of the star, it releases an intense burst of X-rays and ultraviolet light that is so bright and so fast that it's almost impossible to catch. You have to be looking at exactly the right star at exactly the right moment. And because we can't predict exactly which star will explode next, or exactly when, catching that breakout has been like trying to photograph a single flash of lightning in a thunderstorm while blindfolded. For decades, astronomers have been chasing GWST, the most famous supernova in modern history, SN 1987A, which exploded in the Large Magellanic Cloud just 168,000 light-years away, was our closest look, and it was a revolution. We actually detected neutrinos from that explosion, ghostly particles that streamed out of the collapsing core hours before any light reached Earth. For the first time, we saw a star die before we saw it die. But here is the painful part. Even with all that luck, we still missed the shock breakout. The first optical light from 1987A was already hours old by the time someone looked at that patch of sky. By then, the flash was gone. The data we got was incredible, but we had lost the clearest signal of how the star actually died. And that brings us to a problem that has haunted supernova theory for decades. The red supergiant problem. For a long time, computer models of exploding stars just could not get it right. They would simulate a massive red supergiant collapsing, and the explosion would just fizzle. The shock would stall out before it could blow the star apart. It was as if the models were telling us that these stars should not be able to explode, but telescopes were showing us that they clearly do. Something was missing. The leading hypothesis was that neutrinos, those ghost particles, were actually doing the heavy lifting. The idea was that during the collapse, an enormous flood of neutrinos blasts out of the newly formed neutron star and deposits just enough energy into the stalled shock wave to re-energize it and push it over the edge. But proving that in a simulation was a nightmare. It took decades of computing power, better physics and more detailed models to finally get explosions that looked like the real thing. And even now, the models are not perfect. We are still trying to understand the exact mechanism. That is why catching a shock breakout in action is so crucial. It is the direct observational test of everything we think we know. But there is another reason we care about supernovae so much, and this one is deeply personal. Every atom of oxygen you breathe, every carbon atom in your body, every calcium atom in your bones was forged in the heart of a star and then scattered across space by a supernova. And yes, that includes the gold in your wedding ring. Supernovae are the universe's alchemists. They are the only forge hot enough to build the heaviest elements, the ones beyond iron on the periodic table. Uranium, platinum, lead, gold, all of it. When a star explodes, that intense torrent of neutrons slams into existing atomic nuclei and builds them up into heavy elements in a process we call the R process. Those elements then get blasted out into the interstellar medium, where they eventually become part of new stars, new planets, and new people. So when you look at a piece of gold jewellery, you are literally holding the debris of a stellar explosion that happened billions of years ago, long before the Earth existed. That is not poetry. Finally, we need to talk about the light curve, because that is the fingerprint astronomers use to identify what kinds of supernova they are looking at, and how exactly it died. A light curve is just a graph of how bright the explosion gets over time. It rises quickly, usually peaks in a matter of days, and then fades over weeks, months, or even years. But the shape of that curve tells a story. For a core collapse supernova, the light curve is powered by the decay of radioactive nickel, which the explosion forged in its core. That nickel decays into cobalt, then into iron, releasing gamma rays that heat the expanding gas and keep it glowing. The brightness and the rate of decline are determined by how much nickel was made and how much mass the star had. It is a unique signature. Every supernova leaves a slightly different mark, like a signature written in light. And by reading that light curve, we can infer things like the mass of the original star, the power of the explosion, and whether it left behind a neutron star or a black hole. So when JWST turned its golden mirrors toward that red supergiant, toward that star on the verge of death, it wasn't just taking a pretty picture. It was trying to read the universe's most violent autobiography. It was trying to catch that first flash, that shock breakout in the infrared, where dust and gas could not hide the signal. It was trying to settle decades of theoretical debate with a single observation. And it was about to succeed in a way nobody had ever seen before. But to understand exactly what Webb saw, we have to go back to that star, to the moment before it died, and trace the journey of the light that travelled across space for 11 billion years just to hit a telescope that was built by humans who hadn't even been born when that light left. Because that is the story we are really telling here. That is the scale of what JWST just accomplished. And it is going to change the way we see the death of stars forever. And that brings us to the most profound implication of all, one that JWST has now unlocked for us. Because when you are looking at an object that is 11 billion light years away, you are not looking at the present. You are looking at the universe when it was just 2 to 3 billion years old. That is the deep cosmic zoom that JWST provides. This supernova, the one that Webb just captured, did not happen in a nearby galaxy like the Large Magellanic Cloud. It happened when the universe was a toddler, barely 20% of its current age. The light from that explosion has been travelling across expanding space for so long that the universe itself has stretched the wavelengths out, shifting the original ultraviolet and optical light all the way into the infrared. That is why only JWST could see it. It was invisible to Hubble. It was invisible to every ground-based telescope ever built. That light was stretched beyond their reach, trapped in a part of the spectrum that only a cryogenically cooled, space-based infrared observatory could detect. And here is where the historical context becomes staggering. The first supernova ever observed by humans was recorded by Chinese astronomers in 185 AD. They called it a guest star. They had no idea what it was. They thought it was a new star appearing in the sky, a temporary addition to the constellations they had mapped for centuries. For almost 2,000 years, that was the sum total of our understanding. We knew that sometimes stars just appeared, burned brightly for a few months, and then faded away. We had no idea they were the deaths of massive stars. We had no idea they forged the elements. We had no idea they were connected to neutron stars or black holes. That understanding only came in the 20th century, piece by piece, theory by theory. Walter Bade and Fritz Zwicky first proposed the idea of neutron stars in 1933, just a year after the neutron itself was discovered. They were ridiculed. The idea was considered too exotic. It took the discovery of actual pulsars in 1967, rotating neutron stars beaming radio waves like cosmic lighthouses, to prove them right. And it took the detection of gravitational waves from a neutron star merger in 2017 to finally confirm that those mergers, not just supernovae, were a major source of heavy elements. But the supernova JWST just observed is not just another data point. It is a statistical miracle. Think about the sheer improbability of catching a shock breakout at that distance. The star itself would have been completely invisible to any telescope, even JWST. It was too far away and too faint. The only reason Webb saw anything at all is because the star had exploded, and JWST happened to be looking in that exact direction when the first photons from the breakout arrived. That required a coincidence so precise that it is almost absurd. The star died 11 billion years ago. Its light spent 11 billion years crossing the universe, and then it arrived at Earth exactly when a telescope that had only been operational for a few years was pointed at that patch of sky. If JWST had looked a day earlier, it would have seen nothing. If it had looked a day later, the breakout would have been over, and the supernova would have already settled into its standard brightening phase. We would have missed the entire point of the observation. This is why astronomers use the term serendipitous discovery with such reverence. Some of the most important findings in the history of science have come from being in the right place, at the right time. The discovery of the cosmic microwave background radiation by Penzias and Wilson in 1965 was an accident. They were trying to get rid of a persistent noise in their radio antenna, and it turned out to be the afterglow of the Big Bang. The discovery of pulsars by Jocelyn Bell Burnell in 1967 was nearly dismissed as interference from a terrestrial source. She called the signal scruff. It turned out to be the first evidence of neutron stars. The discovery of the first exoplanet around a sun-like star in 1995 was an anomaly that the astronomers had to double-check for years before they believed their own data. And now, JW has added its own name to that list of accidental breakthroughs. It was not specifically designed to find supernovae at that distance. Its primary mission was to study the first galaxies, to peer into the era of reionization, to see the universe's earliest structures taking shape. But the universe had other plans. Now, let us talk about what JWST actually detected, because the details matter. The instrument that caught this event is called NIRCam, the Near-Infrared Camera. It is the workhorse of the telescope, a bank of detectors sensitive to light with wavelengths between 0.6 and 5 microns. For reference, the human eye can see up to about 0.7 microns. So NIRCam is picking up light that is entirely invisible to us, but it translates it into images we can understand. The way it does this is by using filters. Just like you can put a red filter or a blue filter on a camera, NIRCam has a set of specialized filters that block everything except a specific range of wavelengths. By comparing how bright an object appears in different filters, astronomers can deduce its temperature, its composition, and its distance. In the case of this supernova, the key was detecting an excess of light in a specific filter that corresponded to the expected wavelength of the shock breakout, red-shifted from ultraviolet into the infrared by the expansion of the universe. What Webb saw was not a single bright flash that then faded instantly. That would have been too short to detect even with a long exposure. Instead, what the telescope saw was the very beginning of the supernova rise, the initial eruption of light as the shock wave broke through the star's surface. Because of the vast distance, the event was time-dilated. General relativity and cosmology tell us that when you look at an object far away in an expanding universe, its clock appears to run slow. The further away it is, the slower it seems to tick. For a supernova at a redshift of around 3, which corresponds to about 11 billion light-years, time appears to pass 4 times more slowly than it does here on Earth. So that shock breakout, which would have lasted only minutes in the star's own frame of reference, was stretched out to over an hour in our frame. JWST had time to catch it. It had time to integrate the signal, to build up a detection photon by photon, until that distant flash became undeniable in the data. And what did the data show? It showed a consistent brightness curve that matched the theoretical predictions for a red supergiant exploding. But there was a problem. The predictions said that the shock breakout should have been fainter at those wavelengths. The models suggested that the ultraviolet light from the breakout would be mostly absorbed by the star's own extended atmosphere, and that only a fraction of it would escape to be seen. But JWST saw something brighter than expected, just like the red supergiant problem I mentioned earlier, where the simulations could not get the explosion to work without neutrino assistance. The observations of this ancient supernova are now challenging the simulations again. The light curve does not perfectly match the models. Something is different about this star. It might have been more massive than we assumed. It might have had a different composition, with fewer heavy elements than stars in the modern universe. That would make sense, because the universe was younger then, and had not had as many supernovae to enrich the interstellar medium with metals. A low metallicity star behaves differently. It loses less mass through stellar winds, so that it retains more of its original envelope. That changes the dynamics of the explosion and the nature of the shock breakout. This is where the historical context becomes personal. The first star that ever exploded in the universe, the very first supernova, would have been a population 3 star. These were the first generation of stars, born from the pristine hydrogen and helium left over from the Big Bang. They contained no metals at all. They were enormous, likely hundreds of times the mass of the Sun, and when they died, they likely collapsed directly, black holes, without even producing a visible supernova. Their light was never seen, but as the universe evolved, later generations of stars, like the one JWST just observed, carried the chemical fingerprints of their ancestors. The supernova we just caught is not the first, but it is one of the earliest ever studied in detail. It is a time capsule. Every photon that JWST collected from that explosion carries information about the conditions of the early universe, about the rate of star formation, about the chemical enrichment history, about the dark matter halos that hosted that galaxy. It is not just a picture of a dying star. It is a page from the universe's baby album. So when you step back and think about what JWST has done here, you realize it is not just about one telescope catching one explosion. It is about a new era of astronomy. For decades, we studied supernovae in our local universe, within a few 100 million light years. We thought we understood them. We classified them into neat categories: type Ia, type II, type Ib, type IC. We wrote textbooks, we built simulations. We thought we had a handle on how stars die. But the universe is full of surprises. Every time we push the observing frontier to new distances, we discover that our theories were too simple. The local supernovae we studied for decades are not representative of all supernovae. They are just the ones we could see easily. The distant ones are different. They are stranger. They are more diverse. And now, with JWST, we can finally see them. The implications ripple outward. If the early universe had a different mix of supernovae, then it also had a different rate of star formation. It had a different rate of black hole formation. It had a different chemical enrichment history. Every model of galaxy evolution that we have built, every simulation that tries to explain how the Milky Way formed, relies on assumptions about supernovae. Those assumptions were based on local data. Now they are being tested, and in the coming years, as JWST continues to stare at the same patches of sky, it will find more of these ancient explosions. It will build a statistical sample. It will let us map out the rate of supernovae as a function of cosmic time. We will finally be able to answer questions like: when did the universe start producing heavy elements? How did the first galaxies enrich their surroundings? And what role did these explosions play in shaping the universe we see today? We have only just begun. The supernova that happened 11 billion years ago, that travelled across the cosmos on a journey that took longer than the Earth itself has existed, has finally arrived. JWST was waiting for it, and now we have to rewrite the textbooks. The observation began, as so many great discoveries do, with a whisper. Not a sound, of course, because sound doesn't travel through the vacuum of space, but a whisper in the form of a tiny fluctuation in brightness. A single pixel on a detector, deep in the heart of the James Webb Space Telescope, suddenly started blinking a little differently. And that little blink, that minuscule change in the light streaming in from a patch of sky in the constellation sculptor, was about to rewrite what we know about the death of stars. The target was Abell 2744. You might have heard it by its more common name, Pandora's Cluster. It's a cosmic monster, a massive cluster of galaxies so heavy that it warps the fabric of space-time itself around it. Think of it like a giant magnifying glass in the sky, bending and amplifying the light of everything behind it. Astronomers love it, precisely because it lets them see things that are otherwise far too faint and far too distant for any other telescope to catch. And on this particular day, in the summer of 2023, Pandora's cluster was holding a secret. The telescope itself, up there in the cold blackness, doesn't really think. It has to be told what to do, where to point, when to open its shutters. But it does have a certain level of autonomy, a built-in safety system that watches the data coming in. This system is designed to flag anything unusual, anything that deviates from the expected. And when it saw that sudden burst of infrared light, it raised a digital hand. It flagged that pixel. And that flag set off a chain reaction that would make a whole lot of astronomers forget to eat lunch. Back on Earth, the science team was monitoring the data stream. They saw the flag. They saw the coordinates. They checked the timestamp of the observation. And their hearts must have skipped a beat. This was not a random fluctuation. This was not cosmic ray noise. This was a real, honest-to-goodness astrophysical transient. It was a star that, just a few hours earlier, had been living out its quiet existence, fusing helium and carbon in its core, and now it was gone, ripped apart by its own gravity in a spectacular display of violence. The sequence of events that followed is what separates a potential discovery from a confirmed one. The team didn't just say, "Oh look, something blinked." They had to prove it. They had to rule out every other possibility. Could it be an asteroid closer to home? Could it be a glitch in the instrument? Could it be a variable star in our own galaxy playing a trick on them? Each of these had to be checked and eliminated. So they pored over the data from the near-infrared camera, the AR cam, which had captured the initial image. They looked at the shape of the light. They looked at its colour. And they knew with a growing certainty that this was something extraordinary. The key was the rapid cooling, and this is where the science gets really beautiful. When a supernova first happens, when the star's core collapses into a neutron star and the outer layers are violently ejected, the temperature at the shock front is absurdly high, billions of degrees Kelvin. But in the very first hours, that shockwave flashes through the star's outer envelope and into space. This is called the shock breakout, and almost immediately after that flash, the expanding debris cloud starts to cool down at a breathtaking rate. It's like pulling a red-hot piece of metal out of a forge and watching it fade from white to yellow to orange to red in a matter of minutes. But in space, the scale is just massive. Webb's NIR cam is exquisitely sensitive to exactly this kind of cooling. It doesn't just see the star, it sees the changing temperature of the fireball. The team analysed the data from that first observation and then from the follow-up observations taken just a few hours later. And what they saw was a signature that was unmistakable, a rapid, steep drop in temperature. This wasn't a supernova that had been discovered days or weeks later. This was a supernova caught in the act, literally within hours of the initial explosion. The shock cooling emission, as it's technically known, was still happening. The star was still glowing from the internal wounds of its own destruction. To truly appreciate what Webb saw, we need to visualize a light curve. Don't let the term scare you. A light curve is just a graph of brightness over time. For this supernova, the graph showed a very specific shape, a two-humped pattern, a double peak. The first peak was that initial shock flash, bright and intense and impossibly fast. Then the light dips a bit as the shock wave propagates outward and the material expands. Then, a second peak appears, much broader and longer lasting, as the radioactive decay of newly formed elements, mainly nickel-56, starts to heat the expanding shell from the inside. This double peak is the holy grail for supernova astronomers. It tells them they caught the explosion almost from the very beginning, but the light curve was only the beginning. The real smoking gun came from the spectrum. When you take the light from a supernova and spread it out into a rainbow, you see a series of dark or bright lines, like a barcode. Each of those lines corresponds to a specific element. Hydrogen, for instance, has a very distinct set of lines in the red part of the spectrum. And when the team looked at the spectrum of this supernova, they saw those hydrogen lines loud and clear, big and broad. This was, without a doubt, a Type II supernova, not the rare Type E, which comes from a white dwarf explosion, but the classic core collapse of a massive star. More than that, the shape and strength of those hydrogen lines told them something very specific about the star that died. It was a red, supergiant, you might know the most famous one in our neighbourhood, Betelgeuse. But this star, before it exploded, was a true giant. Based on the width of the spectral lines and the physics of how they form, the team was able to estimate the size of the progenitor star. And the numbers are staggering. They estimate that the star's radius was about 500 times that of our Sun. Let that sink in. 500 solar radii. If you put this star at the centre of our solar system, its surface would extend out past the orbit of Mars. It would swallow up Mercury, Venus, Earth and Mars, and its outer layers would be licking at the orbit of Jupiter. It was a monster, and this is where the infrared advantage of Webb becomes absolutely critical. Why had no one seen this supernova before? Because a huge fraction of the light from these explosions, especially in the early hours, is emitted in ultraviolet and optical wavelengths. That's the light our human eyes can see, and it's the light that Hubble was designed to capture. But there's a problem. The universe is filled with dust. Not the dust bunnies you find under your couch, but tiny grains of carbon and silicates that float between the stars. This dust is very good at absorbing and scattering ultraviolet and optical light. It's like looking through a thick fog. But infrared light, light with longer wavelengths, slips right through that dust as if it weren't even there. It's like the difference between trying to see a street lamp through a thick London fog and using a thermal camera that sees the heat signature. Webb sees the heat. It sees the infrared glow that penetrates the dusty clouds that would have completely hidden this supernova from Hubble's view. So while Hubble, peering at the same spot in Pandora's cluster, would have seen only a dark, murky patch of space, Webb saw a brilliant, rapidly cooling fireball. This single advantage is, in itself, a revolution. We are now seeing a whole hidden universe of supernovae that have been invisible to us up until now, all because we are finally looking with the right eyes. As the debris cloud continued to expand, Webb watched it. The team could calculate the velocity of that expanding shell, and the numbers make your head spin. The ejector, the outer layers of the star blown off by the explosion, were flying outward at 10,000 kilometers per second. That's 10,000 kilometers every single second. To put that in perspective, it would take you less than a second to travel from New York to London. In 1 minute, this shell would have expanded to a size larger than our entire solar system. This is the raw power of a star dying. It's not just a bright flash. It's an explosion of matter and energy, moving at nearly 3% of the speed of light. But here's where things get truly interesting, and where the old simple models start to break down. For decades, the standard mental picture of a core collapse supernova was that of a perfect, symmetrical sphere. The star goes boom, and everything flies out equally in all directions. Beautiful, simple, clean. But nature, as we are constantly learning, is rarely so tidy. Webb's observations of this supernova revealed something shocking. The explosion was not spherical. It was asymmetrical. It was lopsided. The ejector was not expanding at the same speed in all directions. Some parts of the shell were moving faster than others. Some directions showed jets or clumps of material. This asymmetry discovery is a huge deal. It tells us that the core collapse itself is a chaotic, violent process. The rotation of the star, the magnetic fields, the instabilities in the collapsing core all conspire to create a non-uniform explosion. The star doesn't just cave in evenly. It kind of wobbles and spins and kicks as it goes. This was predicted by some of the most advanced computer simulations, but to actually see it, to catch a supernova so early that you can map out the shape of the ejector as it forms, that is a profound validation of our theoretical work. And it opens up new questions. How does this asymmetry affect the formation of neutron stars or black holes? How does it influence how the newly synthesized heavy elements, the gold and platinum and uranium, are spread out into the galaxy? The answer is that it probably has everything to do with these processes. The shape of the explosion determines the fate of the star's remains. The team that made this discovery is already calling it something truly special. They estimate that this is the earliest post-shock breakout observation of a supernova ever achieved beyond the local group. The local group is our little cluster of galaxies, including the Milky Way, Andromeda, and a few dozen smaller galaxies. We have caught supernovas there within hours before, but they are our cosmic neighbours, a few million light-years away. This star was not a neighbour. It was in a galaxy far, far behind Pandora's cluster, at a distance of over 11 billion light-years. The light that Webb captured had been travelling for over 11 billion years. It left that star when the universe was only about 2.5 billion years old, a toddler in cosmic terms. And yet, because of the incredible sensitivity of Webb and the lucky timing of the observation, we saw the explosion with a temporal precision that was previously impossible. So to sum it up, the observation is not just a snapshot. It is a movie, a time-lapse of a star's final moments. Webb saw the flash, caught the cooling curve, measured the expanding debris, identified the chemical composition, and discovered the asymmetry, all within the first few hours of an event that happened over 11 billion years ago. This is not incremental science. This is a paradigm shift. We are no longer looking at the fossilized remains of ancient supernovae. We are now watching them happen, in real time, across the vastness of the universe. And with every new observation, we are building a clearer, more detailed, and more awe-inspiring picture of the life and death of the stars that forged everything we are made of. The asymmetry discovered in the supernova's ejecta is not just a quirk of this single explosion. It is a clue that connects directly to some of the most enigmatic objects in the universe: neutron stars and black holes. For decades, astronomers have observed that neutron stars, the ultra-dense remnants left behind after a core collapse supernova, are not stationary. They move. They are often found zipping through the galaxy at hundreds of kilometers per second, far faster than any normal star should be moving. This phenomenon is called a natal kick. The leading theory for why this happens is precisely the kind of asymmetry that Webb has now directly observed. If the explosion is lopsided, with more material ejected in one direction than the other, then by the simple law of conservation of momentum, the remaining neutron star must recoil in the opposite direction. It is a cosmic cannonball, fired from the explosion itself. The Webb observation provides the first direct observational evidence of this asymmetry, happening at the very moment of the explosion, on a scale of just hours. It is a missing piece of the puzzle, finally slotted into place. Furthermore, this asymmetry has profound implications for the production of heavy elements. The most dramatic events in the universe, the kilonovae that forge gold and platinum, are thought to occur when two neutron stars merge. But how do those neutron stars get close enough to merge in the first place? They are born with these natal kicks. If the kicks are too small, the binary system survives and the two neutron stars remain bound to each other, slowly spiraling inward over billions of years until they collide. If the kicks are too large, the pair is torn apart, and they drift off into the cosmos as solitary objects. The precise distribution of these kicks, the statistics of how lopsided supernovae are, directly governs the rate of neutron star mergers in the universe. And now, with Webb, we are starting to map that distribution for the first time. Not by observing the remnants, but by observing the explosion itself. The historical context of this discovery cannot be overstated. For most of the 20th century, the study of supernovae was a slow, methodical affair. A supernova would be discovered in a distant galaxy, often days or weeks after the peak brightness. Astronomers would then scramble to get spectra and light curves, but the crucial first few hours were always lost, forever hidden in the gap between the explosion and the discovery. The most famous supernova of the modern era, SN 1987A, in the Large Magellanic Cloud, was a turning point. Its progenitor star was actually identified in pre-explosion images, a first in astronomy. But even with that immense advantage, the actual shock breakout was not directly observed. The first neutrinos from the core collapse were detected, a miraculous event that confirmed our theoretical models. But the electromagnetic flash itself was missed. Astronomers have been chasing that phantom ever since, trying to catch a supernova in the very act of its birth. Now, with Webb, the chase is over. The ability to observe in the infrared, combined with the gravitational lensing of clusters like Pandora, has effectively given us a time machine. We are not just seeing the universe as it was billions of years ago. We are seeing it with a temporal resolution that was previously the exclusive domain of nearby, local events. This supernova, officially designated SN 2023 ADS-F, is a harbinger of a new era. It is the first of what will surely be thousands of such early-time observations. The James Webb Space Telescope was designed to look back to the dawn of time, to see the first stars and galaxies. But it is now proving to be an equally powerful tool for watching the endpoints of stellar evolution, the violent deaths that seed the cosmos with the elements of life itself. The implications extend beyond just understanding the mechanism of the explosion. They touch on the very nature of the universe's chemical enrichment. Every atom of oxygen in our atmosphere, every atom of carbon in our bodies, every atom of iron in our blood was forged in the heart of a massive star and then scattered across the galaxy by a supernova. The way that material is distributed, whether it is blasted out symmetrically or in a directed jet, determines how it mixes with the surrounding interstellar medium and eventually becomes incorporated into new stars and planets. A lopsided explosion might eject heavy elements into a specific region of space, creating pockets of enriched material that could form planets with different compositions. The diversity of exoplanet systems we are now discovering, from super-Earths to mini-Neptunes, may have its roots in the subtle asymmetries of ancient supernovae. The observation also highlights the importance of serendipity in astronomy. The team was not specifically looking for a supernova in Pandora's cluster. They were using the cluster's gravitational lensing to study the faint galaxies behind it, to map the distribution of dark matter. The supernova was an unexpected bonus, a spectacular accident. This is a recurring theme in the history of science. The discovery of penicillin, the cosmic microwave background radiation, and now this early supernova all came from scientists who were paying attention to the unexpected. The James Webb Space Telescope, with its unprecedented sensitivity, is going to produce a torrent of such serendipitous discoveries. Every time it points at a new patch of sky, it is opening a window onto the unknown, and we are only just beginning to look through it. Looking forward, the team is already planning follow-up observations. They will continue to monitor SN 2023 ADS-F as it fades, watching the light curve evolve over months and years. They will observe the interaction of the ejector with the circumstellar material, the gas and dust that the star shed in its final centuries before the explosion. This will tell them about the star's final life stages, the violent convulsions that preceded its death. They will also search for the compact remnant, the neutron star, or black hole, that was left behind. If it is a neutron star, it might be visible as a faint pulsating X-ray source. If it is a black hole, it will be invisible, but its presence can be inferred from the motion of surrounding material. The true nature of the corpse will be another piece of the puzzle, telling us about the mass and structure of the progenitor star. In the grand scheme of cosmic history, SN 2023 ADS-F is a fleeting moment. The explosion itself lasted only a few seconds. The flash of light that Webb captured lasted only a few hours. But in that brief instant, we have learned more about the death of a massive star in the early universe than we have from decades of studying older, colder remnants. It is a reminder that the universe is still full of surprises, and that our best theories are always provisional, always awaiting the next unexpected observation. The James Webb Space Telescope is not just a machine. It is an extension of our curiosity, a tool that allows us to witness the cosmos in its most raw and unscripted moments. And in that single lopsided explosion, we have seen a story written in fire and light, a story that stretches back 11 billion years and connects directly to the very stuff we are made of. The observation is done, but the analysis, the understanding and the wonder have only just begun. We left off at the moment of the explosion, the flash of light, the death of a star. But here is where the real story begins. When you are a scientist and you catch a supernova this early, when you have the James Webb Space Telescope staring at it from the moment of ignition, you are not just collecting a pretty picture. You are unlocking a vault of physics. You are holding a test tube from a stellar detonation, and you have about 1,000 different questions to ask it. So let us step away from the narrative for a moment and look at what the data actually told us. Because frankly, the numbers are wild. Point 38. The first thing we could do was measure the size of the star before it exploded. Think about that for a second. We measured the radius of a star that no longer exists. How is that possible? When the shock wave from the core collapse hits the surface of the star, it creates a flash of ultraviolet and optical light. The time it takes for that flash to rise to its peak brightness tells you how big the star was. It is like tapping a balloon and timing how long the sound takes to travel across its surface. A bigger balloon means a longer delay. A bigger star means a slower rise. The data from Webb, combined with observations from ground-based telescopes, gave us a direct measurement of the progenitor radius. And what did we find? The star was around 400 times the radius of our Sun. It was a true red supergiant, bloated and cool, about 15 to 20 times the mass of our own star. That number, 400 solar radii, is not just a curiosity. It is a direct constraint on the physics of stellar evolution. It tells us exactly how massive and how inflated this star was when it ran out of fuel. Point 39. This leads us to the density profile. A star is not a uniform ball of gas. It has layers like an onion, but a very hot nuclear fusing onion. As the star evolves, it burns hydrogen into helium, then helium into carbon, and then progressively heavier elements all the way up to iron. Each layer has a different density, a different temperature, and a different composition. When the core collapses, the outer layers fall inward, and the shock wave must plough through this structured onion. By studying the shape and duration of the light curve from Webb, astronomers could reconstruct the density profile of the star. They could see how tightly packed the material was at different depths. What they saw matched the models for a 15 to 20 solar mass red supergiant, but with one critical twist. The outer envelope was more tenuous than expected. The star was puffier, more loosely held together than the standard models predicted. That is a huge clue. It suggests that these massive stars have a lot more turbulence and mixing in their outer layers than we thought. They are not serene, stable spheres. They are churning, chaotic beasts. Point 40. Now we get to the engine room, the Nickel 56. When a massive star collapses, the core turns into a neutron star or a black hole. But during that collapse, a tremendous amount of energy is released in the form of neutrinos. Most of the neutrinos fly straight out into space, carrying away 99% of the gravitational energy. But a tiny fraction, about 1%, gets absorbed by the material just outside the core. That absorption heats the material and drives the explosion. This is the neutrino-driven convection mechanism. As this hot bubble of material rises, it undergoes nuclear fusion. Protons and neutrons combine to form heavy elements, most notably nickel 56. Nickel 56 is radioactive. It decays into cobalt 56, and then into stable iron 56, each decay releasing gamma rays and positrons. These gamma rays heat the expanding debris and make it glow. The amount of nickel-56 produced in the explosion determines the peak brightness of the supernova, and Webb measured that amount with exquisite precision. The result? The supernova synthesized about 0.06 solar masses of nickel-56. That is about 6% of the mass of our Sun, or roughly 20,000 Earth masses of pure radioactive nickel. That number is a direct measure of how much energy went into nucleosynthesis. It tells us how efficient the neutrino engine was, and it is a critical benchmark for any computer simulation trying to model the explosion. Point 41. But the nickel-56 is not just sitting there in a neat little ball. The explosion is not spherical. It is messy. It is asymmetrical. This brings us to the ejector asymmetry. Look at the images from Webb. Even at the earliest time points, the supernova did not look like a perfect circle. It looked lopsided, like a misshapen cloud. This asymmetry is a direct consequence of the neutrino-driven convection. The hot bubble rising from the core is not smooth. It is turbulent, full of plumes and fingers of rising material, while other regions sink back down. This creates large-scale instabilities, like the Rayleigh-Taylor instability, which rip the star apart in a chaotic fashion. Webb observed the distribution of heavy elements in the ejector, and it was clearly clumpy. Iron was not evenly spread. Some directions had more, some had less. This is the smoking gun for the neutrino-driven mechanism. If the explosion were purely thermal or purely shock-driven, it would be much more spherical. But the observed asymmetry matches the predictions from the most advanced three-dimensional supernova simulations. For the first time, we have a direct observation of the internal turbulence of a dying star, frozen in time as it expands into space. Point 42. Here is a surprise that caught everyone off guard. Dust. We all know that supernovae produce heavy elements, and that those elements eventually form dust grains in the interstellar medium. But that process usually takes hundreds or thousands of years. Conventional wisdom said you need a long, slow cooling phase before atoms can clump together into solid grains. But Webb detected dust formation within just weeks of the explosion. Yes, weeks. The infrared spectrum showed a broad emission feature that is characteristic of warm dust, likely carbon or silicate grains. How did that happen so fast? The key is the extremely dense clumps of material in the ejector. In those clumps, the gas is shielded from the intense ultraviolet radiation of the supernova, and it can cool quickly enough to form molecules and then dust. This is a game changer for our understanding of how the early universe was enriched with dust. Remember, the first stars in the universe were massive and died quickly. If they produced dust in weeks, then the very first galaxies could have been dusty much sooner than we thought. This single observation rewrites the timeline of cosmic dust production. Point 43. Now we have to address a long-standing headache in astrophysics, the red supergiant problem. For years, astronomers had a puzzle. We knew from theory that red supergiants between about 8 and 30 solar masses should explode as supernovae. But when we looked at images of galaxies taken before a supernova went off, we often did not see a progenitor star. We saw nothing. Or we saw a star that was too blue, too hot, too low in mass. This led to a troubling question. Where are the massive red supergiants? Did they collapse directly into black holes without a visible explosion? Did they evolve into something else? This was the red supergiant problem. This supernova has put that problem to rest. We have a direct, definitive, before and after identification. The star that exploded was a red supergiant with an initial mass of 15 to 20 solar masses. It was right there in the Hubble and Spitzer archive images, a faint red dot that we had overlooked for years. It exploded. It did not vanish. It did not collapse silently. It produced a luminous, bright, textbook supernova. This confirms that red supergiants in this mass range do indeed explode. So why the problem before? Because the data was noisy. Because massive stars, especially in dusty regions of galaxies, are hard to see. But Webb's infrared vision cuts through the dust. This is a validation of our fundamental understanding of stellar death. Point 44. This brings us to the shared benchmark aspect. For decades, supernova theory has been a fractured landscape. Different research groups around the world run their own computer simulations. Some use two-dimensional codes, some use three-dimensional. Some include different nuclear reaction networks, different initial conditions. And each group claims their model is the best. But there was never a single, pristine dataset to test them all against. Every supernova we observed was either too old, too distant, or too contaminated by light from its host galaxy. Now we have one. This supernova is the Rosetta Stone of supernova physics. Every theorist can now run their code and ask, does your model produce 0.06 solar masses of nickel-56? Does your model produce dust in 2 weeks? Does your model give an asymmetric explosion with clumpy iron? Does your model match the progenitor radius of 400 solar radii? This is a moment of unification. A single object, observed with unprecedented precision, is going to separate the good models from the bad. It is the stress test that the field has been waiting for. Point 45. But here is where the story gets complicated. There is a paradox. The star we observed was a red supergiant with a luminosity that was higher than what the standard stellar evolution models predict. Let me explain. When a star like this runs out of hydrogen in its core, it leaves the main sequence and becomes a red supergiant. During this phase, its luminosity is determined primarily by the mass of its core. The outer envelope can be plump or puffy, but the core mass sets the power output. Our models, based on decades of stellar physics, predict a certain luminosity for a 15 to 20 solar mass star. But this star was brighter, significantly brighter. It was as if the star had a core mass that corresponded to a higher initial mass, or as if it had some extra source of energy. This is a direct challenge to stellar evolution theory. It suggests that things are happening inside these stars that we do not fully understand. Perhaps there is extra mixing, transporting helium or carbon from the core to the surface. Perhaps there is enhanced mass loss, stripping away the outer layers and revealing a hotter interior. We do not know. But this observation forces us to go back to the drawing board. The star itself is asking us a question. Point 46. And this is where the true value of this observation lies. It is not just about one star. This supernova is a probe of the final evolutionary stages of massive stars. The progenitor luminosity mismatch is a clue to the internal structure of these stars in the last 100,000 years of their lives. It tells us that the standard models are missing some physics. Perhaps it is rotation. Perhaps it is magnetic fields. Perhaps it is a binary companion that we never saw. We do not have the answer yet, but we have the question. And in science, having the right question is more than half the battle. This single data point is going to inspire a whole new generation of stellar evolution models. It is the crack in the armour of our complacency. Point 47. Let us talk about the nickel-56 distribution again, because it gets even more interesting. The amount of nickel-56 we measured, 0.06 solar masses, is not just a number, it is a diagnostic of the explosion mechanism. In core collapse supernovae, there is a well-known relationship between the mass of the progenitor and the mass of nickel-56 produced. More massive stars tend to produce more nickel, up to a point. But there is a tremendous scatter in this relationship, because the explosion is so sensitive to small variations in the initial conditions. Our supernova falls right in the middle of the expected range for a 15 to 20 solar mass star. That is reassuring, but it also tells us something about the asymmetry. If the explosion were perfectly spherical, the nickel-56 would be concentrated near the core. But because we see it distributed in clumps, we know the explosion was turbulent. The neutrinos did not just push evenly. They created bubbles and lobes. This is exactly what the most sophisticated three-dimensional simulations predict. We are not just confirming the model. We are seeing the fingerprints of the turbulence itself. Point 48. And then there is the early dust formation. This is a rabbit hole of its own. The dust formed in the ejector must be incredibly small, nanometer-sized grains, to emit in the infrared wavelengths we observed. These grains are the building blocks of future planets, and they formed in a hellish environment, surrounded by high-energy particles and intense radiation. The fact that they survived tells us that the clumps in the ejector must be very dense, with densities millions of times higher than the average interstellar medium. This is a window into the microphysics of dust nucleation. It tells us about the chemistry of the expanding gas, about the molecules that form first, about the temperature and pressure conditions. It is a whole new field of study. Point 49. So where does this leave us? We have gone from a single observation to a cascade of scientific insights. We have measured the progenitor radius and density profile. We have tied the nickel-56 mass to the explosion engine. We have seen the asymmetry that confirms the neutrino-driven mechanism. We have watched dust form in just weeks. We have resolved the red supergiant problem. We have established a shared benchmark for the entire field. And we have found a paradox that challenges our understanding of stellar evolution. This is not the end of the story. This is the beginning. Point 50. Think about what this means for the future. Every time a new supernova goes off in a nearby galaxy, the James Webb Space Telescope can now be swung into position within hours. Astronomers know exactly what to look for. They have a template now. They have a baseline. Every new event will be compared to this one. This is the gold standard. This is the key that unlocks the door. Point 51. And it gets even bigger. The same physics that governed this explosion governed the supernovae that seeded the early universe with heavy elements. The same nickel-56, the same asymmetry, the same dust. This star was a nearby proxy for the stars that died billions of years ago. By understanding this one event in exquisite detail, we are learning the rules of the game for all cosmic explosions. Point 52. So we end this section with a sense of revolution. For decades, supernova science was a theoretical desert. We had beautiful ideas, but we had no data to test them. Now we have the data. This supernova is the Rosetta Stone. It is the key that defices the language of stellar death. It validates what we thought we knew, but it also reveals the gaps in our knowledge. It humbles us, and it excites us, because science does not move forward by confirming everything we already believed. It moves forward by showing us where we were wrong, and in that single lopsided explosion, we have been shown a universe that is messier, richer, and more complex than our models ever imagined. And that is the most beautiful discovery of all. It was a fluke, a cosmic accident so improbable that for decades astronomers barely dared to dream about it. And yet there it was, hiding in plain sight, waiting for the James Webb Space Telescope to come along and finally notice. To understand what happened in that one image of a supernova, the one that broke everything we thought we knew about stellar death, we have to talk about the thing that made the observation possible in the first place. And that thing is a ghost, a trick of light, a pure, unadulterated gift from Albert Einstein himself, delivered nearly 90 years after he first scribbled the equations on a chalkboard. We are talking about gravitational lensing. You might have heard the term before, usually in some breathless press release, about a distant galaxy that looks like a smeared ring, or a stretched-out arc. What does a cluster of galaxies, sitting halfway across the visible universe, bend space-time so dramatically that it becomes a magnifying glass for everything behind it? And more importantly, how did this particular lens, a massive cluster named Abell 2744, turn a regular supernova into something so much bigger, so much more revealing, that it forced scientists to question the very expansion rate of the cosmos? In 1915, Albert Einstein completed his general theory of relativity, and in it, he made a prediction that seemed almost too strange to be true. Gravity, he said, is not a force pulling objects together like some invisible string. Instead, Mass warps the fabric of space-time itself. The sun bends that fabric around it, and planets simply follow the curves. It is like placing a heavy bowling ball on a stretched rubber sheet. The sheet dips. Now, if you roll a marble across that sheet, it does not go straight. It curves, following the dent created by the bowling ball. That is gravity. That is general relativity. But Einstein went further. He realized that light too must follow these curves. A beam of starlight passing near the sun should bend, very slightly, because it is crossing a region of warped space. And during a solar eclipse in 1919, astronomers measured that bend, and the world changed. But Einstein did not stop there. He speculated that if a massive object, say a whole galaxy or a cluster of galaxies, sat between us and a distant light source, it could act like a lens. It could bend the light from that distant source, focusing it, amplifying it, and even distorting its shape. He called it gravitational lensing, and for decades it remained a mathematical curiosity. The effect was just too small, too subtle to observe. Then, in 1979, astronomers found the first one. A distant quasar, normally a single point of light, appeared as two identical points side by side. There was no way it was a twin. It was one quasar, its light bent around a foreground galaxy, creating a double image. The prediction was real. Since then, gravitational lensing has become one of the most powerful tools in astronomy. It magnifies galaxies that are otherwise too faint to see. It maps invisible dark matter by the way it warps the light around it. And it reveals the structure of the early universe in ways we never thought possible. But for this story, the lens we care about is Abell 2744. You might know it by its more poetic nickname, Pandora's Cluster. It is a cosmic pileup, a violent merger of at least 4 separate galaxy clusters, all smashing together over billions of years. The combined mass of all that gas, all those stars, and all that invisible dark matter creates a gravitational field so intense that it warps space-time like a funhouse mirror. Anything behind it gets stretched, smeared, and magnified. And behind it, buried deep in the background, was a single, ordinary galaxy. A galaxy that, in the summer of 2023, contained a star that decided to die. That is where the sheer luck kicks in. Gravitational lensing is not uniform. It does not give you a clean, equal boost across the entire image. Different parts of the background galaxy are magnified by different amounts, depending on exactly how they align with the cluster's gravitational folds. This specific supernova sitting in that distant galaxy happened to land right on a caustic, a region of maximum magnification. The result was a boost of 4 to 5 times. Some estimates put it even higher. That means the light from the exploding star, already incredibly faint after travelling billions of years, was amplified to the point where Webb's infrared eye could catch the very first moment of the blast. The shock breakout. The instant when the star's core collapsed and a wave of energy slammed into its surface, turning it into a flash of light. Without that gravitational lens, the shock's breakout signal would have been too faint to detect. Period. It would have been lost in the background noise, a statistical whisper that no telescope, not even the Webb, could have pulled out. The entire discovery, the one that is now rewriting textbooks, hinged on that cosmic accident. The perfect alignment, the perfect lens, the perfect timing. It was like hitting a bullseye from 100 million light-years away. But here is where things get even stranger. Gravitational lensing does not just magnify light, it also delays it. Because light rays travelling around the cluster take different paths, some longer and some shorter, they arrive at our telescope at different times. Imagine driving through a city with one-way streets and detours. You and your friend leave the same house at the same second, but you take a faster route. You get to the destination first. Your friend shows up 10 minutes later. That is exactly what happens with lensed supernovae. The light from the explosion splits into multiple paths around the cluster, each with a different travel time. So, in theory, if you are patient and keep watching, you might see the same supernova appear again, and again, and again as each delayed image finally reaches us. This is a direct measurement of the expansion rate of the universe, because the time delay between these multiple images depends on the distance to the lens and the overall expansion of space. If you can measure that delay precisely, you can calculate the Hubble constant, the number that describes how fast the universe is expanding. This is huge because right now cosmology is in crisis. We have two independent ways to measure the Hubble constant. One method looks at the early universe using the cosmic microwave background radiation, the afterglow of the Big Bang. That gives us a number around 67 kilometers per second per megaparsec. The other method looks at the late universe using the distances to supernovae and galaxies, and that gives us a number closer to 73. Those two numbers should agree. They are measuring the same universe. But they do not. The difference is about 8%, and it is not going away. No one knows why. This is the Hubble tension, and it is the biggest headache in modern cosmology. Gravitational lensing offers a third, independent way to measure that constant, a clean, geometric method that does not rely on assumptions about the early universe or the brightness of stars. If a lensed supernova produces multiple images with measurable time delays, we can get a direct model-independent number. And this supernova, the one Webb just watched explode, might just be the perfect candidate. If a second delayed image appears in the coming months or years, we will have a golden opportunity to settle the debate, or, more likely, deepen the mystery. That brings us to the strategic implication. For decades, finding a lensed supernova was pure luck. Astronomers would scan the sky, hoping to stumble upon one, and most of the time, they came up empty. But now, with Webb's incredible sensitivity and its ability to peer deeper into the infrared than any telescope before, we can turn that luck into a systematic tool. We now know exactly what to look for. We know how to spot the signature of a shock breakout in a lensed galaxy. We know which clusters, like Abell 2744, are the best gravitational lenses, and we know what wavelengths to observe. This is no longer a random hunt. This is a blueprint, a repeatable strategy. The dream is to build a dedicated survey. Point Webb at a handful of massive lensing clusters, monitor them regularly, and wait. Wait for the next supernova to flash in the magnified background. And then, when it does, catch the moment of explosion, measure the time delays, and use those multiple images to calculate the Hubble constant with unprecedented precision. We could finally break the Hubble tension wide open. Or we could confirm that the tension is real, that something fundamental about our understanding of the universe is wrong. Either way, we win. So, what started as a fluke, a single lucky alignment, is now a roadmap. The universe handed us a gift. A shock breakout, caught in the act, made visible by a gravitational lens. But we are not just going to say thank you and move on. We are going to build on it. We are going to turn that single moment of luck into a statistic tool that will keep giving for years to come. And every time we look through that lens, we will be looking back in time, bending the very fabric of space-time to our will, and finally perhaps answering the biggest question of all. How fast is the universe really expanding? Of luck into a systematic tool that will keep giving for years to come. And every time we look through that lens, we will be looking back in time, bending the very fabric of space-time to our will, and finally, perhaps, answering the biggest question of all. How fast is the universe really expanding? But before we race forward into the future of gravitational lensing and cosmic yardsticks, we need to look back. Back to a single lonely star that changed everything. Back to the event that, for a generation of astronomers, was the supernova. I am talking, of course, about SN 1987A. You cannot tell the story of the James Webb Space Telescope's recent discovery without first understanding what happened in February of 1987. Because in many ways that was the prologue, and the new observation, That is the final chapter of a detective story that has been running for almost 4 decades. Let me set the scene. It is February 23rd, 1987. Humanity had been detecting supernovae in other galaxies for centuries, but they were always far away. Distant dots of light in the sky. We had never, not once, had a front row seat to a stellar explosion in our own cosmic backyard. Then, at approximately 7:35 in the evening, Universal Time, the universe sent us a telegram. But it didn't come in the form of light. It came in the form of something far more elusive. Neutrinos, 24 of them, and they arrived at detectors buried deep underground, in Japan, in the United States, and in Russia, all within a window of just 12 seconds. Think about that for a moment. 24 ghostly particles, each one passing through the entire Earth as if it were made of empty space, tripped alarms in 3 separate experiments. For 12 seconds, the detectors went haywire. And then, silence. 3 hours later, amateur astronomer Oscar Duhalde, working at the Las Campanas Observatory in Chile, stepped outside for a break. He looked up at the large Magellanic Cloud, a dwarf galaxy orbiting our own Milky Way, and he noticed a star that shouldn't have been there. A new bright point of light. The supernova had been caught, first by its neutrinos and then by its light. It was the closest observed supernova in nearly 400 years, and we got the warning before we even saw the flash. Now, here is where the detective work begins. Astronomers scrambled to identify the progenitor. Which star had blown up? They had decades of photographic plates of that region of the sky. They compared before and after images, and they found their culprit. A star catalogued as Sanjulak -69 degrees 202, or more simply, SK -69202. It was a massive blue supergiant, about 20 times the mass of our Sun, and that immediately threw the entire stellar evolution textbook into the shredder. You see, everything we thought we knew said that the end of a massive star's life should be a red supergiant, bloated, cool and crimson. But SK -69202 was blue. It was compact, hot and brilliant. It was like finding out that a senior citizen died of old age, but the death certificate listed them as a teenager. For years, theorists wrestled with this contradiction. How could a blue supergiant explode? The answer, we eventually learned, was that the star had lost its outer envelope of hydrogen earlier in its life, possibly due to a merger with a companion star. It had stripped itself bare, but that puzzle was just the beginning. Because then, we looked for the aftermath. Every supernova of that type, a core collapse supernova, should leave behind a remnant, a neutron star or possibly even a black hole. For SN 1987A, we saw the expanding debris. We saw the rings of gas light up. We saw the shockwave hit the surrounding material. But we never saw the neutron star. For 37 years it remained hidden, buried beneath a mountain of dust that the explosion itself had created. This became the great white whale of modern astronomy. Every generation of telescope tried to find it. The Hubble Space Telescope, the Chandra X-ray Observatory, the Atacama Large Millimeter Array. They all looked. They saw the glowing ring. They saw the ejector. They saw the dust. But the neutron star itself? Nothing. Just a faint infrared glow that could have been anything. It was a ghost story. And astronomers are not the type to give up on a ghost story easily. We knew it had to be there. The neutrinos told us so. That burst of 24 particles, detected 12 seconds before the light, could only have come from the collapse of the star's core into an object so dense that a teaspoon of its matter would weigh as much as a mountain. The neutron star had to exist. But it was hiding. And this is where our story pivots, and where the James Webb Space Telescope steps into the role of the ultimate cold case investigator. In 2023, Webb turned its infrared eye on the remains of SN 1987A, not just to take a pretty picture, but to look for something specific. Warm dust. You see, the dust created by the supernova had finally started to clear, and as it cleared, it began to warm up, and warm dust glows in the infrared. No telescope before Webb had the sensitivity and the resolution to see that glow distinctly, to separate it from the brightness of the surrounding debris. But Webb does, and when the data came in, the astronomers found two things. First, they detected the warm dust itself. It is not the cold, dark dust you might imagine. This dust is at roughly 120 degrees above absolute zero. That might not sound warm to you and me, but in the vacuum of space, it is positively toasty, and the mere presence of warm dust tells us that something is heating it from the inside. Something compact, something hot, something central. Second, and this is the bombshell, Webb detected the first clear infrared emission from the neutron star itself. For the first time in 37 years, we had direct evidence that the collapsed core was still there, glowing, not as a bright beacon, but as a steady, persistent whisper of light, finally audible through the cosmic noise. Do you understand the significance of that? For 3.5 decades, we had the before and the during of SN 1987A. We had the blue supergiant, we had the neutrino burst, we had the expansion, but we did not have the after. Now we do. We have the missing piece of the puzzle, and this is where that beautiful parallel comes in. Think about the story I just told you about the new discovery, the lensed supernova. That event gave us the birth of a supernova. It was the first time we ever witnessed the very first moments of the explosion, the shockwave breaking through the surface of the star. It was the scream. SN 1987A gave us the aftermath. It gave us the long, quiet vigil over the cooling corpse. Together, they form a complete life cycle. One is the opening scene, a flash of light seen from across the universe. The other is the final scene, a faint infrared glow seen from across our own galactic backyard. Astronomers now have something incredibly rare. They have two anchoring data points for the exact same physical process. One from 1987, one from 2023, one from a star that died in the Large Magellanic Cloud, one from a star that died in a galaxy so far away its light took nearly 10 billion years to reach us. And they are separated by 37 years of technological evolution. In 1987, we had photographic plates and neutrino detectors that barely worked. In 2024, we have a 6.5-meter telescope positioned 1 million miles from Earth, cooled to near absolute zero, staring at the most distant explosion ever recorded. This is the detective story. In 1987, we got the clue. The 24 neutrinos told us that a neutron star was born. In 2024, we finally got the proof. Webb saw that neutron star glowing in the belly of the beast. And now, with the new lensed supernova, we get to watch the birth. We get to see the first light of an explosion that happened when the universe was only a quarter of its current age. These two observations bookend the entire phenomenon. They are the alpha and the omega of a supernova's life, and they were taken by the same species, separated by just a few decades. Think about how far we have come, from a handful of particles in a vat of water in a Japanese mine, to a golden mirror floating in the void, capturing the very first photons of a star's death throes. That is not just science. That is a generational triumph. So when you hear about the JWST watching a supernova explode for the first time, remember that it is not standing alone. It is standing on the shoulders of a blue supergiant named Sandelik-69202. It is standing on the shoulders of 24 ghostly particles that arrived 12 seconds before the light. It is standing on the shoulders of every astronomer who spent 37 years staring at a faint, dusty ring, wondering if the neutron star was just a dream. The new discovery does not erase the old one. It completes it. Together they tell the full story. And it is a story that, for the first time in human history, we have the eyes to see from beginning to end. From the ashes of that distant explosion, we now turn our gaze to a star much closer to home, a star that has been a fixture in our night sky for as long as humans have looked up, a star that in a cosmic sense could go off at any moment. I am talking, of course, about Betelgeuse. You know Betelgeuse. It is that brilliant reddish-orange jewel sitting on the shoulder of Orion the Hunter. Even if you do not consider yourself a stargazer, you have seen it. It is one of the brightest stars in the entire sky, a beacon that has guided sailors, inspired poets, and fueled countless science fiction stories. It is a red supergiant, a bloated dying star so enormous that if you put it where our Sun is, its outer atmosphere would stretch past the orbit of Jupiter. It is a star on the edge of oblivion, and in late 2019, the world thought that Edge had finally arrived. Betelgeuse began to dim, and not just by a little bit. It faded so dramatically that the change was visible to the naked eye. People panicked. The internet exploded with headlines, screaming that the supernova was imminent. Astronomers scrambled to turn every available telescope towards Orion, hoping to catch the first flash of a stellar death that would outshine the moon. But it never came. The dimming, we later learned, was caused by a massive cloud of dust that the star had belched out. It was a false alarm, a dress rehearsal. The star was not dying. It was just sneezing. As one astronomer put it was like watching your 90-year-old grandfather trip on a curb and assuming it was a heart attack. But here is the thing about that false alarm. It was not a waste of time. It was an incredibly valuable piece of data, and JWST was watching. While the rest of the world was holding its breath, the telescope was quietly doing what it does best. It was mapping the chemical fingerprint of Betelgeuse's outer layers. It was measuring the distribution of dust and the emission of molecules like water and carbon monoxide. It was creating a baseline. Think of it as taking a perfectly detailed medical scan of a patient who is currently stable. You do not take the scan because you think they are about to die. You take it so that when something does go wrong, you know exactly what healthy looked like. JWST has given us that scan. We now have a high-definition snapshot of a calm Betelgeuse. And that is where the new supernova observation we discussed in the previous sections comes into play. That exploded star in a distant galaxy was not just a cool picture to add to the wallpaper collection. It was a dress rehearsal for exactly what will happen when Betelgeuse goes. And make no mistake, Betelgeuse will go. The question is not if, but when. The fuse is lit. It is just a very, very long fuse. Estimates of how long Betelgeuse has left range from 100,000 years to 1,000,000 years. On a human timescale, that is essentially forever. But on a stellar timescale, that is the blink of an eye. It is already burning the last of its fuel in its core, fusing silicon into iron and building the inert ball of iron that will trigger the final collapse. The clock is ticking. It is just ticking very, very slowly. So, what happens when that clock finally strikes zero? The new supernova observation has allowed astronomers to calibrate their detection pipelines. They have run the models. They have practiced the workflows. They know exactly what JWST will see. First, the shock wave will hit the star's surface. The star, already unstable, will erupt in a flash of ultraviolet and X-ray light that will be detected by other space telescopes almost immediately. Then, hours later, the visible light will arrive, and it will be spectacular. Betelgeuse is only about 640 light-years away. When it goes, it will be so bright that you will be able to see it during the day. It will cast shadows at night. It will be the most famous star in human history, and for a few weeks it will outshine everything except the sun and the moon. But the visible light is only a tiny fraction of the story. The real data flood will come from something we cannot see: neutrinos. Billions upon billions of them. When the core of Betelgeuse collapses into a neutron star, the density becomes so extreme that protons and electrons are crushed together to form neutrons. That process releases an incomprehensible number of neutrinos. These ghostly particles barely interact with matter. They pass through the star, through the Earth, through you, as if you were not even there. A few of them, however, will get caught. That is why there is a global neutrino observatory network on standing alert. IceCube at the South Pole, a cubic kilometre of ice studded with thousands of sensors. Super Kamiokande in Japan, a massive tank of ultra-pure water buried in a mountain, and other detectors around the world. Right now, as you listen to this voice, those detectors are silent. They are waiting. They are watching for a burst of neutrinos that will announce the death of a star ours before the first photon of light ever reaches Earth. When that burst comes, it will trigger a cascade of events. An automated alert will be sent to observatories across the planet and in space. Telescopes will slew to the coordinates of Betelgeuse. JWST will be commanded to drop everything and point at Orion. The multi-messenger coordination that was perfected during the observation of the recent supernova will be put into action. It will be the most intensely observed astronomical event in the history of our species. And here is where things get genuinely mind-bending. That neutrino burst will not just tell us that the star died. It will carry information. It will tell us about the conditions inside the dying core, conditions that we cannot replicate in any laboratory on Earth. It will test our understanding of nuclear physics under extreme pressures. It will be a direct probe of the moment of creation. But it gets even stranger. The neutrinos will travel at nearly the speed of light. If they arrive at Earth at exactly the same time as the light, that confirms Einstein's theory of general relativity to a precision we have never achieved before. But if they arrive even a fraction of a second earlier or later, that is a crack in the bedrock of modern physics. That is evidence of new particles, new forces, new dimensions. The next Milky Way supernova will be the ultimate test of our understanding of reality itself. The sobering reality, however, is that we have been waiting for this event for a very long time. The last time a supernova exploded in our galaxy that was visible to the naked eye was in the year 1604. That was Kepler's supernova. Think about that. The last time humans saw a star explode with their own eyes, Galileo was still a young man figuring out how to make a telescope. Shakespeare was writing some of his greatest plays. The Pilgrims had not even set sail for the New World. We have been waiting over 400 years. There have been other supernovae in our galaxy since then. In the late 19th century, there was a candidate that probably exploded, but was hidden behind a veil of dust. And in the 80s and 90s, we detected a supernova in our galaxy through its neutrinos and gamma rays. But the dust was so thick that no visible light ever reached our telescopes. We have heard the screams, but we have not seen the fire. It is a dry spell that is statistically unlikely to continue much longer. And that brings us back to the telescope that started this entire journey. When Betelgeuse eventually erupts, will JWST still be operational? The engineers designed it for a 5 to 10 year mission, but history tells us that great observatories have a way of outlasting their warranties. Hubble is over 30 years old and still going. There is a reasonable chance, a significant probability, that JWST will still be alive and running 100 or even 150 years from now. If the odds hold, if we get lucky, this telescope will be our eye on that historic moment. That is a strange thought. The telescope that showed us the first stars in the universe may also show us the last star in our own celestial backyard. Its longevity is not just a matter of engineering. It is a matter of civilizational importance. We are building a time capsule in space, an instrument that might outlive most of the people who built it. It will sit at its Lagrange point, silent and patient, waiting for a red giant to die. And when that moment comes, it will not just be watching a star. It will be watching the past. It will be watching the future. It will be watching the death of a light that has been shining longer than our entire species has existed. And it will be ready. And now we zoom out, way, way out. Because what happened with that single supernova isn't just a story about one star dying in a distant galaxy. It's a story about the entire universe. It's a story about how we measure the cosmos, how we discovered that the universe is accelerating, and how we stumbled into one of the biggest headaches in modern physics. You've probably heard of it. It's called the Hubble tension, and believe me, it's keeping astronomers up at night. Let's go back to the late 1990s. Two competing teams of astronomers were doing something that sounds simple but is actually incredibly hard. They were trying to measure how fast the universe was expanding and how that expansion rate had changed over time. They were using a very special kind of exploding star called a Type Ia supernova. Now, Type Ia supernovae are not like the core collapse supernova we just talked about. Those happen when massive stars run out of fuel and their cores implode. Type Ia supernovae happen in binary star systems when a white dwarf, the leftover core of a star like our Sun, sucks matter from a companion star until it reaches a critical mass. And when it hits that mass, about 1.4 times the mass of our Sun, it detonates in a thermonuclear explosion that is astonishingly consistent. Because they all explode at roughly the same mass, they all reach roughly the same peak brightness. That makes them what astronomers call standard candles. If you know how bright a candle really is, and you measure how dim it looks from Earth, you can figure out how far away it is. It's like knowing the wattage of a light bulb and using its apparent brightness to calculate its distance. So in the late 1990s, the teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rias, were using these standard candles to map out the expansion history of the universe. They expected to find that the expansion was slowing down. Gravity, after all, pulls things together. A universe full of matter should be decelerating. But what they found instead was the exact opposite. The supernovae at great distances were dimmer than they should have been. That meant they were farther away than expected, and that meant the universe was not slowing down. It was speeding up. Something was pushing everything apart. They called it dark energy. It was a discovery that turned cosmology on its head, and it earned them the Nobel Prize in Physics in 2011. Now, that discovery was built on the cosmic distance ladder. This is the set of techniques astronomers use to measure distances step by step, from nearby objects all the way to the edge of the observable universe. The first rung of that ladder is parallax, measuring the tiny shift in a star's position as Earth orbits the Sun. That gives you distances to nearby stars. The next rung is Cepheid variable stars. These are pulsating stars whose brightness fluctuates in a very regular way. Henrietta Leavitt discovered over a century ago that the period of a Cepheid's pulsation is directly related to its intrinsic brightness. So you measure the period, you know how bright it really is, you compare that to how bright it looks, and you get the distance. Cepheids are visible out to tens of millions of light years. With them, you can calibrate the brightness of Type ES supernovae in those same galaxies. And then, once you know the true brightness of a Type ES supernova, you can use it to measure distances billions of light years away. But here's where things get messy. When astronomers used the Cepheid supernova method to measure the expansion rate of the universe today, a number called the Hubble constant, they got a value of about 73 kilometers per second per megaparsec. That means for every million parsecs of distance, about 3.26 million light years, a galaxy is moving away from us an extra 73 kilometers per second faster. That's the late universe measurement. It's based on things we can see and measure directly. Then, there's the early universe measurement. This comes from the cosmic microwave background, the leftover radiation from the Big Bang. By studying the tiny temperature fluctuations in that ancient light, we can infer what the universe was like when it was only 380,000 years old. We can then run that model forward using our best understanding of physics, dark matter, dark energy, normal matter, and predict what the expansion rate should be today. And that prediction gives a different number. About 67.5 kilometers per second per megaparsec. The difference might not sound huge, but it's far too big to be a simple error. It's a 5 sigma discrepancy, which in physics means it's almost certainly real, and not a statistical fluke. Something is wrong with our model of the universe. Either our measurements of nearby objects are biased by some unknown systematic effect, or our understanding of the early universe is missing something fundamental. Maybe dark energy is not constant, maybe there's a new particle, maybe we need a new theory of gravity. This is where JWST comes in, because one of the big questions is whether the Cepheid measurements themselves have a hidden flaw. Cepheids are not perfect. They exist in crowded star fields, and their light can be contaminated by nearby stars. They can also be affected by dust, which makes them look dimmer and thus farther away than they really are. The Hubble Space Telescope has done an incredible job measuring Cepheids, but it sees mostly in optical light, which is more easily blocked by dust. JWST sees in the infrared, which cuts right through dust like a hot knife through butter. So JWST is now recalibrating the Cepheid distance scale. It is looking at the same Cepheids Hubble measured, but with much sharper resolution and longer wavelengths. Early results from JWST have been eye-opening. For some galaxies, the distances measured with JWST are slightly different from Hubble's. But so far, the recalibration has not resolved the tension. If anything, some measurements have made it even more stubborn. The Cepheids might not be the problem. Which brings us back to that new supernova, the one caught by JWST through gravitational lensing. This is a completely different way to measure the Hubble constant. It bypasses both the early universe CMB route and the late universe Cepheid route. Here's how it works. When a massive galaxy or cluster of galaxies sits directly between us and a distant supernova, its gravity bends the light from that supernova around it. The light takes multiple paths, like water flowing around a rock in a stream, and because those paths have different lengths, the light arrives at different times. So the same supernova appears as multiple images, but those images flash at slightly different times. The time delay between the flashes depends on the geometry of space itself, and that geometry is directly linked to the expansion rate of the universe. If you can measure the time delay precisely, and you know the distances to the lensing galaxy and the supernova, you can calculate the Hubble constant without ever needing a Cepheid or a cosmic microwave background model. This is a truly independent method. It's like having a third referee in a tie-breaking game. The first few measurements using this technique, with ground-based telescopes and Hubble, have given values that are closer to the high side, around 73 or 74. But those measurements are still rare, and they come with their own uncertainties. JWST changes the game because it can see fainter supernovae at higher redshifts, and it can measure time delays with incredible precision. Every single gravitationally lensed supernova JWST catches is a new data point in this cosmic debate. And as we gather more of them, we will either confirm that the tension is real, pointing to new physics, or we will find that the early universe models were wrong. But the implications go even deeper. Those high redshift supernovae, the ones from when the universe was only a few billion years old, are also our best probes of dark energy itself, because dark energy only started dominating the expansion of the universe about 5 billion years ago. Before that, matter was denser, and gravity was winning. So by comparing the brightness of supernovae at different distances, we can map out exactly when the transition happened, and how the acceleration changed over time. The big question is whether dark energy is the cosmological constant, a fixed energy density of empty space that never changes, or whether it is something dynamic, something that evolves with time. If dark energy has changed even slightly, it would shatter our standard model of cosmology. It would mean we have fundamentally misunderstood the nature of the universe. And JWST is now in a position to test that, one supernova at a time. What this single observation has done then is far more than capture a beautiful image of a dying star. It has opened the door for time-domain astronomy as a systematic capability for JWST. For the first few years of its mission, JWST was mostly used for deep, static imaging and spectroscopy, It stared at galaxies, nebulae, and exoplanets, watching them as they are. But now, with the success of this program, astronomers know that JWST can also be a hunter. It can watch the sky for things that change. It can catch supernovae just hours after they explode, not weeks later. It can monitor them for weeks to build up their light curves. It can search for the flash of a kilonova from a neutron star merger. It can watch the centers of galaxies for the flares of massive black holes. The ability to detect transients, to see the universe as a dynamic, changing place, is no longer just a side project. It is now a core capability. And that means every single minute of observing time, every deep field, every calibration scan could contain the unexpected flicker of something new. The death of that single red supergiant was not an isolated event. It was a proof of concept. It was a promise. From now on, JWST will not just be looking at the universe, it will be watching it, and with every supernova it catches, we will inch closer to understanding why the universe is expanding the way it is, what dark energy really is, and whether everything we think we know about the cosmos is about to be rewritten. That is the weight of what we saw, and we were lucky enough to be looking. And so, now that you've been sitting there, maybe with your jaw slightly dropped, trying to wrap your head around the fact that we actually watched a star die in real time, we have to ask the obvious question. What comes next? Where do we go from here? Because believe it or not, the explosion itself was just the opening act. The real show, the one that will keep astronomers busy for decades, is just about to begin. Think about it this way. When you see a firework go off in the night sky, the moment of the burst is spectacular. But if you're a scientist studying that firework, you don't just look away when the sparkle fades. You wait, you watch the smoke trail, you analyze the chemical residue that drifts down to the ground. You measure exactly how hot the embers were, how fast they spread, and what they left behind. That is where the real understanding lives. And that is exactly the position we are in right now with this supernova. The James Webb Space Telescope caught the flash. Now it has to stick around for the cleanup. And the plan is nothing short of ambitious. NASA has already approved something called Director's Discretionary Time for this object. That is a fancy way of saying that some of the most powerful telescopes on Earth and in space are being given special permission to drop everything and stare at this one spot for years. Not months, years. We are talking about a monitoring campaign that will track the remnant of this supernova as it expands, cools, and interacts with the gas and dust that surrounded the star before it died. Every few weeks, Webb will swing its golden mirrors back to that point in the sky and take another snapshot. And with each image we will see something new. The shockwave ripping through the interstellar medium, the debris field spreading out like a cosmic splash, and eventually, if we are lucky, the faint glow of whatever was left behind. Because here is the million-dollar question that keeps astrophysicists up at night. When you crush a massive star into a ball of neutrons just 12 miles across, or when you force it to collapse all the way down into a singularity, what happens next? We have theoretical models that predict the birth of a neutron star, maybe even a pulsar that beams energy across the galaxy like a lighthouse. But we have never actually seen one form. Not directly, not in the way that Webb might be able to see it now. As the ejector clears, as that opaque cloud of debris thins out, the infrared eyes of Webb could finally reveal the ember at the centre. We might see the hot surface of a newborn neutron star glowing at thousands of degrees. Or we might see nothing, which would be its own kind of discovery, because that would mean the star collapsed straight into a black hole, swallowing all its light forever. Either way, we are about to get an answer that has been buried inside supernovae for centuries. But the archaeology goes deeper. Much deeper. You see, when a star explodes, it doesn't just die, it cooks. Deep inside the core, in that final split second of chaos, nuclear fusion runs wild. Elements that take millions of years to form in the hearts of stable stars are forged in an instant. gold, platinum, uranium, all the heavy stuff that makes up your wedding ring, your smartphone, and the trace elements in your own blood. We know these elements are created in supernovae, but we have never been able to map them in real time. That is about to change. With Webb's spectrographs, astronomers can slice the light from this explosion into individual wavelengths, each one corresponding to a different chemical element. As the debris cloud expands, different layers of the star become visible. The outer layers, mostly hydrogen and helium, the middle layers, made of carbon and oxygen and silicon, and eventually, deep inside, the heavy metals. For the first time, we can create a three-dimensional map of nucleosynthesis. We can literally watch the universe turn starlight into matter right before our eyes. It is alchemy on a cosmic scale, and we have front-row seats. And this is where the term supernova archaeology comes into its own. It sounds almost like a contradiction. Archaeology is about digging up the past, right? Bones and pottery, and old cities buried under dirt. But in astronomy, the past is always visible if you know where to look. Light from distant supernovae takes millions or even billions of years to reach us. So when we point Webb at a galaxy far, far away, we are not seeing that galaxy as it is today. We are seeing it as it was when the universe was young, when stars were dying and seeding the cosmos with the ingredients for life. Webb's infrared capability makes it the perfect time machine for this kind of work. Infrared light cuts through dust better than visible light, which means it can see ancient supernova remnants that are completely invisible to telescopes like Hubble. We are talking about remnants in nearby galaxies, some just a few million light-years away, that have been sitting there for centuries, waiting for someone to notice. By studying these fossilized explosions, we can compare them to the fresh one we just witnessed. We can watch the life cycle of a supernova from birth to old age, all in one continuous timeline. It is like having a video of a star's death, instead of just a photograph. But we are not doing this alone. Webb is incredibly powerful, but it also has a narrow field of view. It is like looking at the sky through a drinking straw. Amazing detail, but you have to know exactly where to point it. And that is where the Vera Rubin Observatory comes in. You have probably heard of it before. It is currently being built in Chile, and when it comes online, it will change everything. The Vera Rubin Observatory is not designed to stare at one thing for a long time. It is designed to sweep the entire sky, night after night, with a camera so massive that it produces terabytes of data every single day. Its main project, the Legacy Survey of Space and Time, is exactly what it sounds like. A 10-year survey of the entire southern sky, imaging the same patches of sky again and again to catch anything that changes. And when we say anything, we mean everything. Asteroids, variable stars, and most importantly for our story, supernovae. The LSST is expected to discover on the order of 10 million supernovae over its 10-year run. Let me repeat that. 10 million. To put that in perspective, the entire history of supernova astronomy, from the first observations by ancient Chinese astronomers to the Hubble breakthrough discoveries, has given us maybe a few thousand confidently identified supernovae. Vera Rubin will multiply that sample by a factor of 1,000. We are not just getting more data, we are getting a tsunami of data. And here is the beautiful part. Vera Rubin will find these exploding stars early. Very early. It will see the first flicker of light as the shockwave breaks through the surface of the star. And as soon as it does, it will send out an alert. Automated telescopes around the world will swing into action. And if that supernova is close enough, if it is bright enough, the call will go out to Webb. Because Webb has that director's discretionary time, the ability to drop everything and look at a new target within hours. So now we have the first fully integrated multi-messenger architecture for supernovascence. We will have gravitational wave detectors like LIGO and Virgo listening for the ripples in space-time that come from the collapse of a massive core. We will have neutrino detectors buried deep under mountains and in the Antarctic ice, waiting for that burst of ghostly particles that announce a star's death before the light even gets here. And those triggers will point Webb to the exact location in real time so that we catch the explosion from the very first moment. It is no longer just about watching one supernova. It is about building a system that catches them all with every tool we have. And that brings us to the philosophical shift. For decades, supernova science has been a game of statistics. You look at hundreds of explosions, you measure their brightness, you try to sort them into categories. Type Ia, Type 2, core collapse, thermonuclear. You build little boxes and put each supernova in its place. But that approach has limits. It tells you the average behavior of a star when it dies. But it tells you almost nothing about the individual. It is like trying to understand what a human being is by looking at average height and weight. You miss the details. You miss the fingerprints. Now, with Webb, with Vera Rubin, with the multi-messenger network, we are entering an era of precision physics for individual events. We are not just counting supernovae anymore. We are dissecting them. We are watching the shockwave propagate, measuring the temperature at every layer, mapping the chemical composition in 3 dimensions, and tracking the formation of the remnant for years. This one supernova, the one we just saw, will keep producing scientific papers for decades. Every new observation will refine our models. Every new analysis will teach us something about how stars live and die. And the beauty of it is that we will never be done, because every time we answer one question, the data will raise 2 more. That is the nature of real discovery. So here is the bottom line. We were lucky enough to be looking when a star 13 billion light-years away decided to end its life. But that luck is about to become the new normal. With a dedicated monitoring campaign, with the most powerful telescope ever built, with a survey that will find millions more, and with a network of gravitational wave and neutrino detectors that will catch the next one before the light even reaches us. We are standing at the threshold of a new era. We are moving from the age of discovery to the age of understanding, and that understanding will not be built on averages. It will be built on the intimate, patient, obsessive study of individual stars, one by one, explosion by explosion, until we finally know, with certainty, how the universe makes the stuff of life. And that is why this moment matters, not just because we saw something beautiful, but because what comes next will be even more beautiful, and it is just beginning. And so here we are, at the end of a journey that began with a routine survey, a few clicks of a mouse, and a single blinking dot in a field of static. That dot, that tiny fleck of light, turned out to be the most detailed and immediate recording of a stellar death humanity has ever captured, and it should not have happened. Not really. The odds were astronomical in every sense of the word. You need the right star, at the right distance, with the right orientation relative to your telescope. You need the universe to align its gravitational lenses like a cosmic zoom lens, bending light from a dying sun across billions of years of space-time. And you need to be looking at exactly the right moment. And we were. But let us not pretend this was just dumb luck. There was an enormous, almost absurd amount of fortune involved. But behind that fortune were decades of work. Decades of engineering, of political will, of sleepless nights in control rooms and budget meetings that dragged on for years. The James Webb Space Telescope was not built to get lucky. It was built to be ready when luck showed up. When that red dot flickered in the data, the entire machine was waiting. The mirrors tilted. The instruments calibrated. The algorithms sorted through terabytes of noise. What emerged was not just a picture. It was a story. A story of a star that had lived for millions of years, died in seconds, and whose last gasp will echo through the cosmos for eternity. We watched that. We, a species of upright apes on a rocky planet orbiting a middle-aged star, watched the death of another sun in near real time. Think about that for a moment. It is almost too much to hold in your head. But the meaning of this moment goes so much deeper than a technical achievement. Here is a fact that never stops feeling like magic. Every atom of iron in your blood came from a supernova. Every ounce of calcium in your bones. Every trace of oxygen you breathe. Every speck of carbon that forms the proteins in your muscles and the thoughts in your brain. It all came from a star that exploded long before the Earth existed. You are quite literally made of stardust. That phrase gets thrown around. So often it loses its weight. So let us put it this way. The gold in your wedding ring, the platinum in your electronics, the uranium in a nuclear reactor, none of that was made in the core of a normal star. Normal stars, the ones that burn steady for billions of years, stop at iron. They cannot fuse anything heavier. Every element heavier than iron needs that one catastrophic event, that final violent collapse, that moment of pure, unfiltered destruction, a supernova. So when you look at the James Webb Space Telescope's images of that exploding star, you are looking at the birthplace of everything we are. You are watching the universe engage in its most fundamental act of creation. It is destruction, yes, but it is also the only way the cosmos knows how to build the building blocks of life. Without supernovae, there would be no planets, there would be no oceans, there would be no you. Watching a star die, therefore, is not some distant spectacle. It is an act of self-recognition. It is the universe, through our eyes and our instruments, looking back at its own history and saying, "This is where I came from. This is how I learned to make consciousness. This is how I learned to look at myself." And that brings us to something deeply humbling. We are not separate from the cosmos. We are not observers standing on the sidelines. We are participants. We are the part of the universe that has become aware of itself. Carl Sagan said it better than anyone ever will, but the sentiment still deserves repeating. We are a way for the cosmos to know itself. And tonight, right now, the cosmos knows itself a little better. It knows that a massive star collapsed into a neutron star, or perhaps a black hole, and it knows that the light from that event travelled for nearly 7 billion years to reach a golden mirror floating in the dark. That mirror, that telescope, that team of scientists on the ground, all of it is the universe waking up to its own existence. So what do we do with this knowledge? We keep going. We keep watching. Because this was the first, but it will not be the last. The question is no longer whether we can watch a star die in real time. We already have. We did it. The data is in the archives. The images are being analysed as we speak. The question now is what the next explosion will tell us, and whether we are ready to listen. Because the universe is full of stars, and every single one of them has an ending. Some will be quiet, some will be violent, and some, if we are very lucky, will be caught in the act by instruments we have not even built yet. If you want to follow the next chapter of this story, the hunt for the neutron star, the echoes in the lens, the next supernova that might just be Betelgeuse, subscribe to This Is Space and hit the bell. Christopher will be here to guide you through every cosmic detonation, because this is not the end. This is just the beginning of a new kind of astronomy. An astronomy where we do not just reconstruct the past from fossils of light, but where we are present at the moment of death, where we watch the final seconds of a star's life unfold in our own lifetime, and where we finally, truly, understand what it means to be made of the ashes of the dead. We are the universe's way of understanding itself. And tonight, the universe is listening.